발표는 LayerX의 리드 엔지니어인 오스케 수도의 강연을 듣도록 하겠습니다. 주제는 Zerochain, a privacy protecting layer on Substrate using zk-SNARKs입니다. So please welcome Osuke with a big round of applause.
Hi, my name is Osuke Sudo. I'm an engineer in the blockchain space and working at LayerX. LayerX is a blockchain startup based in Tokyo. And we have several projects such as a lot of blocks, but those projects, one of them is Zerochain, which I'm focusing on. So I'm happy to be here to talk about Zerochain. Zerochain is basically a privacy protecting blockchain on top of Substrate. Substrate itself is a blockchain toolkit. So it makes it easy to help you build your own blockchain. And Substrate consists of some Substrate module system. And we are providing especially some Substrate modules and some toolkit for protecting users' sensitive data, which would be stored on-chain. What is the meaning of privacy in the Zerochain context? Our first goal is providing secure and efficient privacy protecting asset protocol on top of Substrate. It means all transfer amount and each account balances and identities of sender and recipient are all private. So in this picture, Alice and Bob have balances, but those balances are encrypted, so no one can see those actual amounts. And in other scheme, identities of Alice and Bob will be also hiding. This is just a diagram, a level overview. Again, we are top of on Substrate, and to get the privacy features, our protocol can be consist of mainly two protocols. The one is ZISA, which is a kind of privacy scheme, and also we use the zk-SNARKs as a knowledge proving systems. And on top of it, we can build a privacy oriented applications such as confidential and anonymous payment applications on top of the Zerochain protocol. So in this talk, let me explain about those main three components, Substrates, these zk-SNARKs, what they are and how it works. The first thing I'm going to talk about what is a Substrate is. Substrate is basically a base blockchain platform developed by Parity Technologies. And it mainly offers some blockchain core components, such as database for storing transactions, peer-to-peer networking to gossip the state transitions, and consensus engine for providing the incentive mechanism in the blockchain network, and transaction queue, etc. So those components might be most complex and difficult part when you're building your own blockchain. But if you build it on the Substrate, you don't need to do that. So those are most complex part. The most thing you need to is that you just build some Substrate modules and Substrate runtime. So these modules can be configured, and runtime is also can be configured like this. So bunch of modules are added to the runtime, like in this code. And there are a bunch of modules. For example, the timestamp module provides just a timestamp in the blockchain. And balances module provides managing fungible assets in the blockchain network. And we especially providing the encrypted balances modules for confidential payment. So what we want to do is that we want to provide the privacy scheme to the Substrate and some Polkadot.net ecosystem using their knowledge proving systems. In this encrypted balances modules, we especially use zk-SNARKs. zk-SNARKs is originally published, it's a paper published by Benedict Burns et al., I think in this February. And it is basically that efficient and free decentralized and confidential payment mechanism that is compatible with a smart contract platform such as Ethereum and Substrate. The basic idea is that the Untitled encryption scheme hides all transfer amounts and account balances, so no one can see those actual amounts. And it takes account-based approach, not UTX approach, for the reason of the efficiency and usability. And it can avoid the UTX accumulations. And in the original zk-SNARK uses a sigma bread, which is kind of the knowledge proving systems, and it is a modified version of the bread proof. But instead, we use the zk-SNARKs for the reason of getting the efficiency in terms of the knowledge proving computation. But the statement itself in the zk-SNARKs are based on the DSA protocol. So let's have a look how it works in this encrypted balance module, as I said. Again, it takes account-based approach and Untitled encryption scheme. And let's think the simple case that Alice sent encrypted 3 coins to Bob. Now Alice has 10 coins and Bob has 5 coins in the mapping structure, same as Ethereum. But obviously, those amounts are public. Everyone can see how much they have currently. So to hide this, we need to hide by some using encryption scheme. So it's encryption scheme called lifted El-Gamal Encryption, especially, which has a homomorphic property. So homomorphic property allows us to compute as a ciphertext. So Alice sends 3 coins as a transaction component into the on-chain, and it will be added to the Bob's encrypted balances and subtracted it from the Alice's encrypted balances. So updated balances will be Alice has 7 encrypted coins and Bob have 8 encrypted coins. So in this computation process done with encrypted, so no one can see those actual amounts. But of course, Alice can see her own balances by using her decryption key, which is kind of her private key. So this is a basic idea of how it works in the Zerochain. But the problem is that how blockchain node can validate this encrypted amount, because it means encrypted amount looks actually like this, just 60-40 byte array. So Alice needs to convince the blockchain node this byte array is actually an encrypted 3 amount. Without revealing the actual amount. So in order to achieve this, we use zk-SNARKs. zk-SNARKs is one of the zero knowledge proving scheme, and it generates some proofs that some statements are actually correct and that provides the private input. So in this context, those statements will be that the transfer amount is in the valid range. So the amount is not overflow or not negative amount. And also Alice has enough balances or not. And it's encrypted by the correct encryption key and so on. So zk-SNARKs allows sender that all the statement is actually correct or without revealing the actual 3 amount. So this is a usage of zk-SNARKs in the Zerochain context. So let's have a look how it works in zk-SNARKs. Basically, zk-SNARKs has 2 players. The one is a prover and the other party is a verifier. And both know the public function f and public input y. And the prover says, oh, I know the private input x, such as fx equal y, and generates proofs and send it to the verifier, and the verifier verify it in the on-chain. So in the previous context, public function f would be that the amount is not overflow or not. And public input x is actual amount, and public input y is encrypted amount, which can be public. But in the pre-processing zk-SNARKs, like growth 16, which is used in the Zerochain, some parameters need to be generated in advance by the trusted setup. So trusted means that we need to trust some authorities, and prover and verifier uses parameters as a proving key and verifying key in order to get make the very small tiny proof size, which would be just 200 bytes, and the verifier can verify the proofs as a succinctness. But why we use zk-SNARKs? Because in the original Zs, I used the sigma red, which is not needed trusted setup. Because we want a quite significantly small proof size and quite efficient verification in order to prove the more complex private computations. And zk-SNARKs has a great community, especially consists of the project they are also using zk-SNARKs. And there are awesome tool chains, mainly developed by zkers, such as pairing-friendly elliptic curves and zk-SNARKs library called Bellman. But again, downside is a trusted setup. But these days, there are some solutions. I'm not going into much details here, but for example, multi-party computation which is done by the Zcash, or universal and updatable SRS, which is called sonic proving systems. So, as a summary, Zerochain protocol can be consist of the hybrid solutions. The currently supported the Ether, which is a high-level privacy scheme, and also we use the Zcash toolchain for the basis zero-knowledge proving systems, and we are top of on Substrate, which provide the core blockchain layer. The next thing I'd like to talk about is that auditability for privacy asset. Because for real-world usage or for enterprise usage, auditability is a quite important aspect. Because we need to protect from the anti-money laundering or some comply with regulations. So appropriate entities should be able to audit certain users' money flow in some financial use cases. In order to achieve this, we prepare a bunch of key pairs, and those key pairs have the specific functionalities, but in terms of the auditability, this decryption key is the most important part because sender passed the decryption key to some auditors. Auditors can decrypt the user's balances by using this decryption key. But auditors cannot spending users' money because they don't have the user's spending key, which is top of left. Because spending key cannot be derived from the decryption key, which is just this arrow is one way. But on the other hand, the decryption key can be derived from the decryption spending key. So this is a key component for getting all the auditability features in their chain. How is the current status of their chain? Our code, our project is all open sourced, so everyone can see our implementation in our GitHub page, LayerX.com/Zerochain, and all the code are implemented in Rust. And this project has been supported by the Web3 Foundation grant program, and you can actually send the confidential transaction to the Zerochain today, but it's still under development for the production ready. We need to get the security reviews and adding more optimization and making some documentations. And we prepared some tools called zface, which is an interface for interacting with the Zerochain. It has a low-level wallet features and some cryptographic tools. You can use command line utilities based in zface today. This is also the open source, so you can find in our GitHub page. For the future works, we are trying to be adding the more interesting functionalities, such as privacy mintable and bannable coins, or the privacy atomic exchanges and multi-signature scheme. And also, we are researching some modules for like the UTXO-based private computations, such as DEXC, which can be more getting the privacy guarantees, but it is overhead is more costly. And I personally implementing the Sonic, which is I mentioned, which is also the type of their knowledge proving systems. This code is also open source, so you can find this in our GitHub page. Yeah, thanks for listening.